Hi everybody, happy e-learning day. So we're going to start our lesson on acids and bases. A lot of this stuff might be review for you, things that you've already known. Some might be new to you, so use as you will. There will be some book problems that'll be assigned for this assignment, but we're going to jump into our chapter 14 here. This particular picture is very apropos. These are called hydrangeas. And the reason why it's apropos for this chapter is hydrangeas change color based on the pH of the soil that they're in. The bluish color, I believe, are in more of a basic soil. They're blue and more basic, and they become pinker in the more acidic soils. So they're really a beautiful flower and a great application of the idea of pH. And then here's our little humor for the day. Alrighty, so let's take a look at what we've got. We have learned this before. There are three different theories of acids and bases. The first one, the Arrhenius theory, is the most limited of the theories, which is where the acid donates a hydrogen ion and the base donates a hydroxide ion. This is limiting in the fact that it is specific only to substances that contain hydrogen ions and hydroxide ions. The second definition is called the Bronsted-Lowry definition, and that's where we look at an acid as being a donator of a hydrogen ion and a base as being an acceptor of a hydrogen ion. We'll use both of these actually more. Sometimes we'll see the Arrhenius theory more than the other, but you do need to be able to recognize both theories. And then the third is the Lewis theory, which is not used as often. I'm not really going to cover it very much at all. There's a section at the end of the textbook that discusses it, but I'm really not going to delve into the Lewis theory, and that is looking at an acid is something that accepts an electron pair and a base is something that donates an electron pair. And you would have to be looking at the Lewis structures to determine those identities. Again, I'm not going to really delve into that. You can learn that when you get into college. All right. So Bronsted-Lowry acids. So here's pretty general definition or equation detailing the acids and bases. You can see how they're all labeled here. The A is just meaning some anion. So we have this acid with that hydrogen out front kind of as the identifying feature of that being an acid. Then we have waters being a base. Now water actually can be an acid or a base. In this case it's a base, and we'll look at why in a second. The result is this H3O ion. If you remember, that's called the hydronium ion. Be comfortable with that term. And then we have this A minus, which is left over. So how do we identify these things underneath here? Really, we look at what's happening from the reactant side to the product side to determine what's playing the acid and what's playing the base role. Bronsted-Lowry, we said an acid is something that donates a hydrogen ion. So if we look here at what happens from HA on the reactant side to what remains on the product side, which is this A minus, we can see that what happened is a hydrogen ion was separated. What remains is simply the A minus or the anion. That hydrogen ion went somewhere. And in this case, it actually went to the water molecule, which then turned into this hydronium ion. So as looking at the changes that occur in this equation, we notice that the HA is the thing that donated the hydrogen ion, so it's behaving as the acid. And on the other side, that water accepted that hydrogen ion, so that means the water must be playing the base role. And then the result is this H3O ion and the A minus ion. Now underneath here we also have a label. We did talk about this, I believe, last year a little bit. Conjugate acid and conjugate base. Now where do those names come from? Okay, so we look at our acid on the reactant side. What remains of it on the product side is called the conjugate base. If you remember from last year, they were found in pairs. So an acid and conjugate base pair. And then the base here, what ends up as a result on the product side of that base is called the conjugate acid. So we have another pair, a base conjugate acid pair. And you will be asked to identify the acid and base conjugate base pair, the base conjugate acid pair, somewhere along the line. So why do we call this an acid and this a base? Notice we have this is a reversible reaction, so we are going to be looking at equilibrium scenarios. But if we read this from right to left, if we reverse this reaction, what we notice then is the hydronium ion is then donating the hydrogen ion, which the A minus is going to accept and turn into the HA on if this were reversible. Okay, then the hydronium ion would be the one donating the hydrogen ion, so it would be playing the acid role, whereas the A minus would be accepting that hydrogen ion, so it would be playing the base role if we reverse this reaction. So that's where those labels come from, but really important that you can identify the pairs within that reaction. The word acid and base are strictly reserved for the reactant side or in the forward reading direction, and conjugate acid and conjugate base are restricted to the product side reading in the forward direction. Okay, so just some information there. Here we've got a molecular diagram of what's going on here. Here is our HA. Here's our water, and we notice that this hydrogen ion here has left this HA and gone to the H2O to give us our hydronium ion, and then that anion is left all on its own. The bottom thing we see here is a simplified version of the above equation. Notice what they've done. If you can pick it out, see what's the difference between them. Hopefully you can see that what they've eliminated is the H2O. So oftentimes they'll shorten the acid-base equation by eliminating the H2O, and then we basically see what is the dissociation of that acid in water. So the HA breaks down into the H plus ion and the A minus ion. I mentioned this earlier, but please remember that there really are not little protons floating around in the aqueous solution when you do have an acid-base reaction. These protons that come off of this acid here actually do go and find a water molecule, and this is really the form, this hydronium is the form that if you were to take a picture of those molecules in that acid solution, you would see them in the form of that H3O ion. We don't see little H pluses floating around. This is just a shortcut form, just abbreviated form, which is often used. Alrighty, so your book talks about what's actually happening. Your book looks at it in this form, is that what's going on in an acid-base reaction is it's a competition for this hydrogen ion. There's two bases in this reaction. Let's go back and look. We have the water as the base and the conjugate base here. They're both kind of vying for the hydrogen ion that comes from this acid. And depending on which of these is the has a greater affinity for that hydrogen ion is going to determine whether our equilibrium position lies more to the product side, the right side, or more to the reactant side. Are we going to make more products when these things come in contact with each other, or are we going to be pretty much in reactant form? So what does it say here? It says if the water has a greater affinity for the hydrogen ion, the water would prefer to be bonded with the hydrogen ion rather than the A minus, then it says the equilibrium lies to the right. So let's go back and take a look. If this water has a great affinity for this hydrogen ion here, then we're going to have a large amount of the hydronium ion and a large amount of this A minus. Okay, so the equilibrium position will lie to the right. Now, if the opposite were true, the A minus has a greater affinity for the hydrogen ion. That means it would rather be attached to the hydrogen ion. Notice what happens. If this A minus really wants to be attracted or attached, bonded to that hydrogen ion, then we're going to have more of this HA and more water, then we're going to have hydronium ions and this anion here. So we would have more reactants, and our equilibrium position will lie to the left. Okay, so that kind of gives us an idea between what are strong acids and weak acids. Okay, strong acids actually have an equilibrium position that lie to the right, so the water has a strong affinity for the hydrogen ion. For a weak acid, the anion, this conjugate base, has a really strong affinity for the hydrogen ion and will actually have more of the HA species present at equilibrium than we have A minus. So we would really not, that acid doesn't dissociate very well, so that would be considered a weak acid. So what you often see is that if we have a strong acid, then its conjugate base is relatively weak. But if we have a weak acid, then that conjugate base is relatively strong. And so we'll see that come up as we go along here. Now what we've got below is our equilibrium expression that we can write from our equations on the previous page. So if we look back at that, if we look at the top equation here, we write the equilibrium expression. Notice both of these would be in the numerator. And then in the denominator, we're only going to see the HA because it's the only species that's aqueous. Remember, anything liquid or solid is not included in our equilibrium expression. So that's where this first one comes from. Okay. The second one is taken from our abbreviated reaction. Let me go back to that here at the base, the bottom of my screen here. Here, these are our products would be in the numerator, and then the HA is in the denominator. So you see, they both are really representing the same reaction. They just are written a little bit different. We have the water eliminated from this hydronium ion and have it just written as H+. This is really the more common version that you'll see when we see this equilibrium expression. Rather than with the water incorporated in that hydronium ion. And notice now we have this little subscript A because we're being specific, talking about an acidic reaction taking place. So the Ka is the equilibrium constant for that. They call that the acid dissociation constant. So a new term, even though we often just say Ka, but it is the equilibrium constant associated with an acid reaction, but the name is acid dissociation constant. So a new term for you to learn. This next example is going to have you practice the concept of acid conjugate base. And so the question is saying, write the conjugate base for each of the following. So I'm going to just show you the first one here. We want to write what the conjugate base is. So that means that this must be behaving as an acid. So what would be its conjugate base? So an acid is going to donate a hydrogen ion. So hopefully you recognize that the conjugate base for this acid would just simply be this with the removal of that hydrogen ion. So I'll write it on the page here, even though it is going to show up later. I'll write that. Hopefully I can write it without making too much of a mess. So I'm going to have ClO4, and the charge is going to be negative on that particle because that hydrogen ion, remember it's an ion, is being removed. That's neutral. We remove something positive, it becomes negative. Looking at letter B here, conjugate base for this acid. We have 3 hydrogens attached here. What we are going to look at is removing 1 hydrogen at a time. And unless they say otherwise, let's just remove 1. This is actually called a triprotic acid because there are 3 hydrogen here. There's a lot of different things that come into play with these. I'm not going to have time to teach all of this to you. But we do we pop off 1 hydrogen at a time. This is a monoprotic acid. It has only 1 hydrogen that will pop off. This one has 3. We are going to look at just 1 at a time. Okay, so what will be the conjugate base for this particular acid? 1 hydrogen is going to pop off. So we're going to be left with H2PO4. This species starts off neutral. We remove a hydrogen ion, and so that leaves a -1 charge there. I could talk, let me just take a brief moment and talk about, well, this acid here then, it's actually a conjugate base, but we'll see a little bit later, this can also behave as an acid. If that were to also behave as an acid, we could write the conjugate base for this, so I'll put a comma here, and that would have the removal of a second hydrogen ion. So what will be left is HPO4 with 1 hydrogen coming off of this species here. And now it's -1 here, but we lost another hydrogen ion, so its charge would be now -2. And then we actually could do that 1 more time, and there would be a conjugate base for this as well. And that would be PO4 3-, and that's your phosphate ion. Here's your hydrogen phosphate ion. Here's your dihydrogen phosphate ion, and then our acid, phosphoric acid. So just a little delving into the fact that that is a triprotic acid, but typically, once again, we would just look at the removal of 1 hydrogen if we were doing this conjugate base problem here. Letter C is a little trickier in the fact that we have 6 hydrogen on there. How do we know which hydrogen is actually going to come off of that particular acid? And keep in mind that it's going to be the bonds that are more polar that are going to be more attracted to water. Okay, having said that, where does this hydrogen ion go? It's going to bond with a water molecule. Where is this hydrogen ion going to go? It's going to go bond with a hydrogen ion, make the hydronium ion. So one of these 6 is going to pop off. It's going to be the one that's in the more polar bond. It's going to be more attracted to the water molecule. So how do we determine that? Well, C is less electronegative than N. If you remember your electronegativity trend on the periodic table, N is more to the right in row 2 than what carbon is, so N's more electronegative. So these bonds, these hydrogen that are bonded to the N's are more polar bonds. These are less polar, so the hydrogens that are bonded in a more polar bond are the ones actually are going to come off more easily than the ones that are nonpolar, because they're not as attracted to the water molecule. So in this instant, the hydrogen that's going to come off is going to come off of the N, not the C. Okay, so what we will have left then is CH3. Those hydrogen don't pop off, and only one of these hydrogen are going to come off. So I'm going to be left with 2 of them. But now this species is positively charged, but I just lost a hydrogen ion, which is positive, so now it's going to remain neutral. And so this would be our conjugate base for this particular acid. Also, if you look in the other direction, this would behave as a base, because we said bases gain hydrogen ions or attract hydrogen ions. So if we went in the other direction, you would see that this particle here gaining a hydrogen acting as a base would turn into this perchloric acid. We have the dihydrogen phosphate polyatomic ion can gain a hydrogen ion and act as a base and turn into their phosphoric acid. And the same thing here with this particle, I'm sorry, I don't remember the name of this, can gain a hydrogen ion and turn into this. So these all going in the opposite direction are acting as bases, hence the name conjugate base. So I hope that helps a little bit with that. It's a common thing to have to do as well, as identify those. All right, so this one is looking at the dissociation reaction of acids. This is fairly common. We've seen this before, but we'll review a little bit. So we just basically want to say what happens to these acids when you place them in water. I'll do a couple of them here, then I'll reveal the answers in a minute. So letter A, we've seen this before. We have HCl. Okay, we place that in water. What is that going to do? The hydrogen ion is going to pop off, and then we're going to be left with a chloride ion in the end. So this is for H+, and this is basically our A- that we saw in the previous equation above. One of the slides earlier anyway. Here we've got acetic acid. Okay, they have this hydrogen separated from the other 3, showing you that this is the hydrogen that's actually going to pop off. It actually is bonded to this O, which is a fairly polar bond rather than any of the hydrogen that are bonded to C. So this actually, even though it doesn't look like it, this hydrogen is actually bonded to an O. Don't have to worry about that right now. But when we write our dissociation reaction for that, we have HC2H3. O2, and that will break apart. This first hydrogen here will break off, giving us H+, and then what remains is our acetate polyatomic ion. Sorry for the scribbles, it looks like I'm right like a 3-year-old. And then here's our anion. Okay, again, this would be our conjugate bases. These would be our conjugate bases, because if we reverse the reaction, they would gain the hydrogen and turn back into the previous form. Letter C, we have ammonium, and that will toggle or turn into NH3, all right, by removing a hydrogen ion. Here we have some lovely acid, don't know the name of it, it'll be in a chart later on in your textbook. The hydrogen will come off of where? The carbon or the nitrogen? Mr. Anderson, can you answer that question? Hopefully you recognize that this hydrogen is bonded to the more polar nitrogen, so one of these is going to pop off. And then this is called a complex ion. We are not going to have time to cover those. This is a common form of aluminum when it's in water, is in this form. So can you think about what would happen with this substance if it's in water and one hydrogen pops off of that? Okay, so think about what that would look like. And then I'll reveal the answers here. Okay, there's our A, there's our B, C. This is the reaction that toggles between ammonium and ammonia. That's that common toggling back and forth. This happens to be a weak acid. This is a weak base. We actually have a strong acid here. We'll talk more about that later. And then acetic acid's a weak acid. Again, we'll address that later. This isn't a amine group, so I don't know if that's a hexylamine acid, something like that. And then here's that aluminum complex ion. One of the water molecules will lose a hydrogen and the other 5 water molecules remain intact. So we've got that Al bonded to with 5 water molecules around it, and 1 water molecule lost a hydrogen ion, so it's in the form of OH, and then our charge went down by 1 because we lost that positive ion. So we are not going to work with complex ions, you guys, but it's a nice little introduction to you seeing those. There's a whole naming system that goes along with complex ions, etc. Okay. All right, so it's 20 minutes in. All right, so let's talk about acid strength. We have seen this before. Strong acids, it says equilibrium lies far to the right. That means you're going to essentially completely dissociate and essentially have no reactant left. They do completely ionize in water. So let's talk about what the K would look like for that. If you have mainly products and virtually no reactants, you're going to have an incredibly huge K. So you really will never see a K reported for a strong acid because they are so large. We essentially say they go to completion, so we don't even really talk about a K for a strong acid. They do have weak conjugate bases because that conjugate base has a really low affinity for the hydrogen ion. The water has a much greater affinity for the hydrogen ion than the conjugate base does. Make sure, you guys, that you're reading your textbook because there is some information that I'm really not giving you that you will need for some of your problems that you're going to do. Okay, so please make sure you read your textbook. And then here below, we have learned these before. Let's look at them again. These are our strong acids. Notice the first 3 here, those are all our hydrohalic, you'll see that word in a minute, acids. They all have halogens in it. Notice the one halogen that is not present here is fluorine. Fluorine is not a strong acid. It is very corrosive, but it is not strong. It does not completely dissociate. That doesn't mean that it isn't harmful. Okay? And then we've got these other 3 acids, H2SO4, which is your sulfuric acid found in your car. Your lead storage batteries in your car have sulfuric acid in it. Nitric acid, I can't think of a everyday place where you would find nitric acid. It dissolves a lot of things, so it is a pretty corrosive acid. I use it to clean when I can't ever get certain materials off of my glassware. I use nitric acid to dissolve that material. And then this one is our perchloric acid. Again, I can't think of a specific everyday household item that would have perchloric acid, but you guys can look that up if you're really interested. So we do have to memorize these 6, excuse me. If you went online and looked up strong acids, you probably will see a few more in this category, but the majority of the chemistry books report these 6 as your strong acids, so I would stick with those, okay? So please make sure you memorize those. All right, what is a weak acid? It's something that the equilibrium position lies far to the left. That means it does not dissociate very much when it's placed in water. Okay, that means its conjugate base has a high affinity for water, or for hydrogen, excuse me. So the conjugate base of a weak acid is actually a stronger base than water. That anion really prefers to be with the hydrogen ion than the water prefers to be with the hydrogen ion. So we'll see this anion really wants to be with that hydrogen ion and stay in this form rather than the water stealing it and taking it away. So this conjugate base is actually stronger than the water is. Take some time and look at the terminology. It does take a while to get used to acid, conjugate base, base, conjugate acid. Those terms are difficult. Spend some time with them, okay? It's not going to happen in an instant. All right, so again, we've got some labels here. With this being a weak acid, that means it prefers to be in this form rather than the dissociated form. So our equilibrium position is going to lie to the left here. We're going to have more reactants than we're going to have products. Okay, this conjugate base, excuse me, is stronger than the conjugate base of the water base, excuse me. All right, so nice little molecular diagram depicting the difference between strong and weak acids. All right, pretty pictures here. You can notice that from this first circle here, they're all bonded together. In the second circle, when you place them in water, they all dissociate. They're all separate. That would be a strong acid. Notice the concentration amounts here. HA, before they dissociate, after the hydrogen ion concentration and the anion concentration are essentially equal to the original concentration that you put in the water. For your weak acid, I don't like the fact that they use a B because that can be deceiving, thinking that's a base, but it is. The anion is behaving as a base. So we have them all bonded together. When you place that in water, most of them would prefer to stay bonded. The conjugate base here really has a high affinity for the hydrogen ion, so they're going to stay in that form, and only a couple. Actually, this picture only shows one of those molecules breaking apart. So how do the concentrations of each species compare? With a weak acid, most of the HB do not break apart, so their concentration is still fairly high, where you have a really low concentration of hydrogen ion and the conjugate base here, the B minus here. So it gives you a nice difference between what your strong acid and weak acid are. Nice table. Please take some time and look at this. I don't need to read it all to you. As far as your homework is concerned, there are a couple of problems that you really will need to make sure that you pay attention to this, okay? Especially when they ask you to talk about rank the bases in terms of strength when you're looking at conjugate bases and acids, that kind of thing. So please make sure you pay attention to this. Remember, we talked about the Ka for a strong acid is very large. Most tables you won't even see a Ka reported for a strong acid. Weak acids is where what you'll see listed in the table. Okay, so take a look at that. Here's some terms for you. Oxyacids are just basically your acids that have polyatomic ions in them, and the hydrogen are bonded to the oxygen. There's a section near the end of the chapter that we can maybe look at some structures if we've got time. Organic acids have something called a carboxyl group. You can see a picture of that in your textbook, what that carboxyl group looks like. That would be your acetic acid, and as an example of an organic acid. They're typically weak. Your hydrohalic acids I mentioned before are those that have halogens in them. They're all strong except for HF, hydrofluoric acid. We talked about monoprotic acids and then polyprotic acids. Let me write that in there. Polyprotic. That means you have more than one hydrogen attached to that anion, and they can pop off in succession. That has an effect on different K values. There's a different K value for the first hydrogen that pops off. There's another K value for the second hydrogen that pops off, etc. So there's a whole section that talks about that. Now, I don't have time to go through example 14.2. Make sure you read through it. It does apply this table 14.2, which we'll see on the next slide, which is simply an ordering of some common monoprotic acids and their strength. They give you the formula, give you the name, and then they give you the Ka values. All right. Remember, the larger the K value, the more the equilibrium lies to the right. Think about that. So if you have a larger K value, that means you tend to make more product. So this would be a stronger acid than the ammonium is. Look at the K values, okay? Much more product for this guy than these guys down here, okay? So equilibrium position lies a little bit more to the right at the top of the table, more to the left at the bottom of the table. Notice the arrow here, increasing acid strength. So at the top, they're stronger acids, and as you go down, they get weaker. These are all relatively weak, I guess you could say, especially compared to strong acids, okay? Then you will have a problem in your textbook where you're going to compare the conjugate bases of these acids. We just went over conjugate bases. Remember, we would remove the hydrogen ion for the conjugate base. Well, if you're a stronger acid, you have a weaker conjugate base. So if we had an arrow here, this would be increasing conjugate bases. So these guys would have a stronger conjugate base than these at the top. So think about that when you're going to look at those problems in your assignment. Okay. So important table for you to keep in mind. All right. Another vocabulary term for you. This is amphoteric. And this is something that is a species that can behave as an acid or a base. Water is an example of that, and that is how we can actually, that's really where all this pH idea comes from, is the fact that water is amphoteric. So that means water can either act as an acid, it can donate a hydrogen ion, or it can act as a base, it can accept a hydrogen ion. Okay, so here's an example. I wish they had both water molecules written out here, H2O plus H2O, then it would be easier to see how one is gaining a hydrogen ion and one water molecule is donating a hydrogen ion to result in a hydronium ion and a hydroxide ion. But this is called self-ionization of water, or sometimes called auto-ionization, because water just on its own in nature does this to a very small extent. So water molecules, you have it sitting in a glass, and over time you will accumulate a few hydronium ions and a few hydroxide ions. It's just a natural thing that it does. Okay, what scientists have discovered is that in water, they've measured the concentrations of these hydrogen and hydroxide ions that are present, and that's where we get this Kw, the water equilibrium constant, if you will. It's called the ion product constant. If you see that down here, that's the name of this Kw. Noah, you were asking about this the other day. So ion product constant is this Kw. You would also call it the equilibrium constant for water. So here's our equilibrium expression right here for our water ionization, then it goes self-ionization, then it goes through. We have the H3O plus times OH minus. Notice there's no denominator because this is liquid, right? So that doesn't get written in our equilibrium expression. What's the difference between this guy and this guy? Look at it. They've eliminated the H2O out of the hydronium ion. So instead of having written hydronium ion, they've written the shortcut version, which is simply the hydrogen ion. This is the form that you will typically see. That doesn't mean you won't see this first version. All right. And then any solution is neutral when the hydrogen ion concentration equals the hydroxide ion concentration. Then you have a neutral solution. Now, let me say, the only time you can have an acidic or basic solution is if it's aqueous. You have to have water present. You're not going to have an acid or base solution with something that's oil as the solvent. So you do need to have water as a solvent to be talking about pH and pOH and being acidic and basic and neutral, that kind of thing. All right, so in pure water, I told you that they've measured the hydrogen ion concentration and the hydroxide ion concentration. They are equal to each other when in pure water, and that concentration is 1 times 10 to the negative 7th. You might want to memorize that number. That is really small, you guys. That's not very much at all, but it is measurable, and it is how we base our pH scale. Okay. This is also at 25 degrees Celsius. It doesn't say here, but this is true at 25 degrees Celsius. If we change the temperature, which you have a couple example problems and a couple of problems in your homework, this is going to change. And you need to be able to understand how that is. And that's going to be based on this Kw and how temperature changes, shifting with your Le Chatelier's principle, all that fun stuff. Okay, but again, here is the actual term for Kw, the ion product constant. So what is that number? Okay, if in a neutral solution, if both of these are 1 times 10 to the negative 7th, then we want to solve for the Kw using this expression above. We end up the Kw is 1 times 10 to the negative 14th, again at 25 degrees Celsius, And that's the majority, 99.9% of your problems you're going to be working, you're going to be at 25% or 25 degrees Celsius when you're dealing with acid and base problems. All right, at least at this level. Okay, so neutral solution, hydrogen ion concentration equals hydroxide ion concentration. You guys probably know that already. What is that concentration? 1 times 10 to the negative 7th at 25 degrees Celsius. So what is an acidic solution? That's where you have more hydrogen ion present than you have hydroxide ion present. So what would be our concentrations? hydrogen ion concentration will be larger than 1 times 10 to the negative 7th. Be careful with those negative exponents. They can get tricky. Really think through that, you guys. Basic solution is the opposite, where your hydroxide ion concentration is larger than our hydrogen ion concentration. So that means your hydrogen ion concentration is less than 1 times 10 to the negative 7th molar. Okay, and we'll see how that plays into our pH system. I want to keep an eye on the time. It's been 33 minutes already, you guys. So in this example, they want us to calculate the hydrogen ion or the hydroxide ion concentration for the following and explain whether they're neutral, acidic, or basic. This is where we are going to employ our K expression. You're going to use either one of these, either this first one here, whichever one you prefer, or this second one. If we know the hydrogen ion concentration, we know the Kw, we can find the hydroxide ion, and then vice versa. We know the Kw. If we know hydroxide, we can find the hydrogen ion concentration by simply doing a little division problem. So let's take a look. Our first example, we have 1 times 10 to the negative 5th molar of hydroxide ion concentration. We want hydrogen ion concentration. Plug that into your Kw expression. You're basically taking your Kw and dividing it by this to get your hydrogen ion concentration. All right, so we can see that in a minute. I didn't work it out here, but here's our expression. We plug in Kw, 1 times 10 to the 14th. We plug in this concentration here, and we can solve for hydrogen ion concentration. So you do that for all of those, and then the result are the following values. So we'd have the hydrogen ion concentration, this is the hydroxide ion concentration. Then to determine whether basic, acidic, or neutral, we look at the size of those. Letter A, we have a larger amount of hydroxide than we have hydrogen ion, so that's basic. And letter B, we have the same amount of both hydroxide ion and hydrogen, so that's a neutral solution. And then in letter C, we have a lot more hydrogen ions than we do hydroxide ions, so that's going to be an acidic solution. So hopefully you can be comfortable with using that. Then I have a reference here to page 660 to 661. This is talking about Le Chatelier's principle and how changing the temperature will affect the Kw. Please read through that exercise. There is one problem in your homework assignment that is in reference to that, so make sure you double check that, okay? I want to get through the pH scale so that on Monday we can continue on with weak acids and bases, etc. So the pH scale, this probably is fairly familiar for some of you. I think we did a little last year. This is looking at the power of the hydrogen ion concentration. It is a log scale, so we are going to do our logs. If you remember doing that, negative log of the hydrogen ion concentration gives us our pH. Okay, then we can look at how that relates to what pOH is and how you can toggle back and forth between hydrogen ion concentration, hydroxide ion concentration, pH, and pOH. And it's a pretty simple relationship. You just have to make sure you remember it. All right, here's our equation for pH. It is the negative log of the hydrogen ion concentration. So if our hydrogen ion concentration is 1 times 10 to the negative 7th, we want to find the pH. We're going to take the negative log of that. Make sure you know how to do that on your calculator. Practice it, you guys. The other thing is whenever we have, take the log of a number where the coefficient is 1, the log, negative log, is simply the exponent. If this coefficient is not 1, then we have to either do our mental math like you saw in, I don't know, a couple months ago already, or resort to our calculator for that. All right, but whenever this coefficient in the front is 1, our pH is simply the opposite sign of our exponent here. All right, so pH is a negative log of that, but make sure you know how to use your calculator. You guys plug this in and practice. Don't just assume, oh yeah, I know how to do that, and come time for your test, All right, so our pH is 7.00. Now, significant figures, your favorite thing in the world. I think there's a rule for everything for significant figures. All right, so for logs, when we do the log, what we do is we look at our original concentration, and we look at how many significant figures are there. There are 2. That means in our log, we should have 2 decimal places. So if there were 3 significant figures here, I would have 3 decimal places in my log. Okay, so that's our rule for significant figures and logs. Easier to do it that way. It's a little trickier the other way. If we've got pH and we're going to our hydrogen ion concentration, then we have to think, oh gosh, what do I do? There's 2 decimal places, so I want 2 significant figures in my hydrogen ion concentration. All right, so keep that in mind. All right, so what is POH? It also is the negative log of the hydrogen ion concentration. Okay, so we can also find POH doing it that way. And then there's another relationship that we'll see when we talk about the pH scale. Now this is another application of a negative log scale, I guess, and we can do the negative log of our K values as well. Some of those K values get pretty small, so sometimes it's a little easier to talk about pK instead of our K values. And again, remember, this would be the exponent that goes along with that particular K value. pH scale. The lower the pH, the greater the hydrogen ion concentration. Okay? Low pH, high hydrogen ion concentration. So here's our nice little scale here, corresponding to our blue with our litmus paper and our red. So blue for basic, red for acidic. Give you some examples of some pH of these things. Notice milk, you might be surprised, is slightly acidic. Okay, just interesting to see this. Our stomach acid, which is hydrochloric acid, is a pH of 2. All right, that's pretty low pH. Okay, so interesting for you to look at. So let's go back here. I should say the higher the pH, the more basic it is. Now, it is possible to have a negative pH, and it is possible to have a pH greater than 15. So I don't want you to think that the scale stops here. These are just the more common numbers that we use. All right, and then how that corresponds to the actual concentration. Okay, notice when we change our concentration by a factor of 1/10, our pH changes by a factor of 1. All right. So this example here, we need to calculate the pH or the POH for each of the following. Actually, they want it for both. All right, so here we have the hydroxide ion concentration, and we want the POH and the pH. We haven't talked about the relationship between pH and POH. We will in a minute. But what we would probably do here is to find our P8. Well, we could find POH. All right, so that would simply be the negative log of, oops, sorry, that's my phone. My sister. Okay, so let me erase this. Go back here. Sorry, you guys. Eraser. Okay, so we're going to do the negative log. Oh, did I get it? Yeah, okay. Negative log of 1 times 10 to the negative third. Okay, and that's going to give us a POH of, can you do that in your head? 3. Now, if we wanted the pH, at this point, all I've told you is we could find that by taking our 1 times 10 to the negative 14th, which is our KW, dividing it by our hydroxide ion concentration, and that'll give us our hydroxide ion, our hydrogen ion concentration, get your words right here, and that would give us 1 times 10 to the negative 11th. That would be our H plus concentration. But if I wanted my pH, I would take the negative log of 1 times 10 to the negative 11th, and that pH will equal 11. Okay, now what you might notice here, some of you already know this, POH and pH, you add those two numbers together and you get 14. You get 14. Notice that number corresponds to our KW exponent. Okay, we take the negative log of our KW, we get 14. So the POH and the pH should always add up to 14 if we're looking at 25 degrees Celsius. That's another way you can toggle back and forth between these different properties that they may ask you to do. So this next one here, we want to know the POH, or sorry, pH. You take the negative log of that, And then now that I told you the relationship between pH and pOH, all you'd have to do is take your pH and subtract that from 14 to get your pOH. My husband's going to work, so goodbye. Love you. Okay. So there's a little explanation there for how those all work together. I'm going to just kind of scroll through the rest of this here. This scale is imperative, and I would learn this one. I wouldn't worry so much about this side, okay, as long as you know how the pH relates here. pH of 7 is neutral, pH less than 7 is acidic, pH greater than 7 is basic. That shouldn't be new to you guys, right? But make sure you know that. This can be more confusing, so as long as you know how to toggle between pH and pOH, then this scale is perfectly sufficient for you. And then there's that really helpful relationship between pH and pOH that will help you toggle between, you should now be able to go between hydrogen ion concentration, hydroxide ion concentration, and then you should also be able to go between pH and pOH, okay, and how they all link together. Play around with that. Make sure you're really comfortable with that, okay? I think that's where I'm going to leave you tonight. I've gabbed at you long enough. That has been 44 minutes. You guys are great. Look on Canvas for what book problems correspond to this, all right? See y'all later. Good night.